welcome everybody for this webinar on CIVA thermal testing. I have shared some slides, so we will start with a few slides like this before showing you directly the software. Okay, so we are going for about 1 hour meeting, I think, on this topic. Okay, let's go. So we're going to talk about CIVA, and more precisely CIVA thermal testing, a new module in CIVA. We'll start with a short introduction to EXTENDE company in CIVA, but quite briefly, and then we will speak in more details about this module for thermographic testing simulation. I will show you a couple of examples. I will show you the capabilities that we have in the current version of CIVA TT. And after that, we will take time for questions and answers using the chat tools of your WebEx window. Again, if you have some questions, I will take time at the end to answer you, at least to try to answer you. So EXTENDE, most of you, I think, already know us quite well, at least a little bit. So we are an NDT engineering company based in France. Mission, let's say, is to bring the benefits of modeling to ND people and to try to, through modeling, to help people develop new methodology, new inspection techniques, and to reach maybe more reliability and help the world to be a safer place. So our activities are mainly focused around the CIVA software. We are the worldwide distributor of CIVA. We are also in charge of the technical support of all CIVA users worldwide. We also provide some training sessions on CIVA, and also we provide a training session on reliability in NDE, dealing with POD and justification, technical justifications, and so on, this kind of topic. We also provide some consulting. We can do simulations for you. We can do trials for you if you prefer us to subcontract your needs in ND developments or qualifications and so on. And another branch of our activity is around the trendy brands, the trendy products. So trendy is different from CIVA. It's I think, completely different. This will be not the topic today. Trendy is a simulator to help people practice UT, practice RT through a virtual environment, virtual simulator. It's I think also an interesting tool for training operators. But let's focus on modeling today on CIVA and maybe CIVA thermal testing. A few words about the CIVA software. It's a simulation tool dedicated to NDE modeling, also analysis. You have different modules available in CIVA. CIVA UT, CIVA X-ray, CIVA eddy current, CIVA guided wave. We also have quite recent modules for structural health monitoring by guided waves. And recently, last year actually, a new module came on. It's CIVA TT for thermographic testing. So it's really a new module within the CIVA platform that we will introduce today. Let's also mention that CIVA can perform some analysis for UT. You can also load real data in CIVA UT. This is something which is today only for the UT parts. Let's also mention the capabilities to run CIVA through scripts. I will briefly introduce this at the end of the session. This is a feature that can be available for any of the techniques, UT, APT, eddy current, and also TT. So capabilities to drive CIVA through scripts. But we'll start by introducing the use of CIVA through the user interface, and CIVA, the ND-oriented user interface, we'll see that. CIVA software remains completely developed by the CEA, French R&D center, and so EXTENDE is the exclusive distributor. So why simulating ND? Why simulating thermal testing more particularly? Well, the idea is to provide a virtual prototyping tool, virtual designing tools, so that you can try, check, maybe make some mistakes, but virtually on the computers before going to the real test. And we hope it will help you to save money at the end. You can, for instance, compare different excitation modes, try different heating times, depending on the materials, the type of defects. You can try to investigate defects and so on. Different techniques can be tested. You can easily vary some parameters, so you can actually really explore a wide range of different setup testing scenario to maybe converge to an optimal one, or at least to give you the most promising solutions before going, of course, to your real test, to the real implementations. You cannot do everything virtually, of course, but by the way, modeling inspections should help you to better understand, better master what you are doing when you develop certain procedures, and maybe to save time and money. In the context also of qualification, using modeling can be interesting because you will have to justify the impact of some parameters when you are involved in such qualification projects, which could involve a lot of mock-up tests if you do everything with physical prototypes, physical mock-ups. You can monitor parameters by simulations. It can be really interesting for that. And it can help you to give some arguments, some elements for technical justifications works. And generally speaking, simulation software should help to make things visual. So to help people discuss together about technical setups and so on, and maybe to convince about a certain solution. Training also can be a reason to use modeling. So CIVA TT, this is the first version within CIVA of this modeling software for thermal testing. It deals with mainly optical heating, active thermography inspection module, so flash lamps, halogen lamps, and so on. Let's mention that for the moment, it's only 2D computations. CIVA TT also includes induction heating module, let's say induction thermography, but for the moment, for this part, only the excitations is simulated actually. The power density induced by the inductor can be predicted and calculated by CIVA TT, but not the thermal part. For optical heating, the full thermal process is modeled. We will see that. So it covers different techniques. You can also change some parameters, component geometries, type of defects, and so on. We will see that directly in the software. I think it's more efficient. So let's go for a demo. I open my CIVA window. You should see now on your screen a new window. This is CIVA 2021 and SP1, so the current commercial release of CIVA. You can see here that it includes different modules. One is TT. You have the other techniques that we have mentioned. So in CIVA TT, you find mainly two, let's say two tiles here, two menu, induction heating simulation and inspection simulation. For induction heating, so let's say relates to induction thermography. We will see that we can do with these modules. Inspection simulation relates to optical heating thermography. I start with induction heating simulation. Maybe I will directly open one example. There we go. So for induction heating, as I mentioned, I have just a warning from David about maybe trouble to hear me. Is it the same for other people, or is it okay? Just to check if you can hear me at least. Okay. Some other people tell that it's okay, so maybe it's just It's okay. Okay, thank you for the other. Tell me, okay. Okay, so let's continue like this. I'll try to speak louder maybe. So in induction heating modules, actually what you can do is to define an inductor, define a zone in which you want to simulate the excitations and visualize the way you induce power in this part. And of course, it will be then the source of heating transfer. But for the moment, in this heating part, only the inductive excitations is simulated currently. It will come in a future release also regarding the thermal part. So you can see here an example with an inductor with a yoke like this on a planar component and a zone in which you can compute the power induced. But you have different panels in CIVA, some of you may know, in which you can play and change parameters. And of course, you can here change the inductor type. You have many different type of inductors. Yoke is one of them, but you can also see here coil with different shapes, cylindrical, rectangular. So let's change this, for instance, only to a cylindrical one, just to show you that, okay, you can change the parameters, the dimensions, and define your own inductor. In terms of component in this module, you can deal with a planar slab like this, but you can also find in the list other geometries, cylinders, for instance, or also, let's say, a blade root, for instance, some geometries of parts that you can also, in which you can simulate the excitations, the power density induced by an inductor. Okay, if I come back to my case, so here it corresponds to a planar slab of steel, and we have tested how we induce here power for different frequencies, 10 kilohertz, 50 kilohertz, and 100 kilohertz, and typically it gives you some charts of the induced power. So here, this is mild steel, so you can see some cross section, and you can see here that it's really limited to the skin depth in this case because of the materials. Okay, and you can see that at the top surface you have some kind of certain distributions of power density that you can visualize. Okay, in the 3D view like this or in some cross sections. You can compare different frequencies together here. So 10 kilohertz here, for instance. Another one, okay, 50 kilohertz, which change also not only the skin depth, but also the way it is distributed. And you can also compare with another material, for instance. Let's say you use the same inductor, but in Inconel. You can visualize here the distributions in Inconel. Okay, so less homogeneous power density induced, but of course, due to different skin depths, you have here more power induced in the cross section of the component in terms of here penetration depth. So this module can help you to see for different inductors, different frequency, the way and the locations of the power induced. And of course, it will be then it will affect the thermal process. Okay, so briefly on this induction part, so only limited for the moment for this part to the heating process, the induction process. Let's now focus on the main part of CIVA-TT, which is the optical heating technique. This is the module here, inspection simulation. So I'll start this second part of CIVA-TT. There we go. Back in the CIVA window, I have here a page in which I can define all input parameters. To do this, I have some panels available at the bottom for specimen, source, detector, and so on. Let's describe them. So, first one, specimen. You can here define the specimen geometry and the material. For this first version of the optical heating module, only planar slab can be defined. You can change the length, the width, and the thickness of them by playing with the parameters. Just have to fill in the menu. You can also, if you have multi-layers specimen, define here 2, 3, 4 layers, and you will have the possibility to change properties for the different layers here. We'll see an example later. So you define like this geometry of your component. Second tab, material properties. So to simulate the heating process, we need here the thermal properties, the thermal conductivity and the heat capacity of the component. Here by default, this is some parameters linked to a carbon epoxy composite component. Okay, this 0.63 watt per meter per Kelvin for the thermal conductivity and this value for the heat capacity. You can define and type your own values if you have data on your materials. You can also rely on a database. If you click open here, you have a couple of examples from metallic materials or other type of materials. You can see the name here and load them into your model. Okay, but you are not limited to this database, provided that you have the values of your specimen. You can here just enter the value you want. Second panel, the source. So the heating source. So here we define the type of excitations versus time. So you can have different type of excitations. You can consider a flash lamp like excitations with an impulse here, impulse heating, where you directly specify the level of energy of heating. You can change here to 6,000 joules, for instance. You have other type of distributions, such as Fresnel, maybe more related to halogen lamps heating with a longer heating process and a certain power that you can also adjust to your case. You define starting time, the end of the heating time. So here, for instance, 4 seconds of heating, if you want. And you can also here find a sinusoidal excitation type for local inspection cases, where you define the frequency here of the heating process in these parameters. I'll start for this case with a flash. So just defining an impulse here and a certain level of energy. In terms of now spatial distribution of the heating process, for this first version, we assume that the top surface of the component is uniformly heated. So we assume that the lamp is somewhere here over the part, and that it's then heats the top surface with this certain level of energy. Okay, so there is no, for these first versions, computations of non-uniform heating process. We assume it's uniformly distributed, uniformly heated on the top surface. The third panel is the detector panel. So the detector panel is symbolized with here this blue rectangle. Okay, you can change its dimensions, define here versus X and Y the dimensions of the detector, so the active part of your detector, and you also define its resolutions by the certain number of pixels along X and Y, as you can see here. Depending on the optical aperture of your heating camera, you can here adjust also the focal distance, and you can see a certain, let's say, zone of sensitivity, which is here plotted, and you can visualize on the 3D view the part of the observed surface that will be then captured by your heat camera. Playing with this. In terms of camera model, we have here different possibilities. You can select the first case, which is a perfect detector. Perfect detector actually assumes that the camera directly converts the observed temperature to a digital level. So there is no specific transfer functions between the observed temperature and the thermogram at the end. So this is the first choice. But you can also here throw an equation or through some calibration curves, define your own heat camera characteristics that will relate the observed temperature to a certain digital level on the final thermogram. Okay. Different capabilities here. That will also affect, the relationships between the temperature of the object, of the observed surface of the object, and the thermogram. This is these parameters here, the emissivity first of the observed surface of the object, that is here by default set to 1, but you can change that value depending on the component surface and so on, and properties. You can also here introduce a certain level of noise that will, of course, define the sensitivity of your camera to a certain noise level. You have also some parameters here for the atmosphere transmission coefficient and also the temperature of an environmental object, a surrounding object, or the temperature that may affect the also the thermogram, especially if you have some reflection on the surface. So depending on the emissivity, this environmental object temperature can affect the final thermogram. So you define that with these parameters here. This is the way the environment is considered in this case, in this version. The inspection panel is just actually a question of positioning the detector versus the component. So here you have a certain distance, let's say. So you can change these parameters. Here, 120 millimeters, for instance. And actually, depending if you have here a positive value or a negative value, you will define if you consider transmission or reflection technique. By putting a negative value, you are in reflection technique because your camera is on the same side as the source, okay, on the top of the component. If you keep here a positive value, the camera is on the other side, so you are in transmissions. Source on the top, camera on the bottom, okay? It's just like this by convention in CIVA. Let's here switch to a reflection-like setup, and let's close that panel. Next panel, this is the defects, the flows. So here, some defects are already created by default. I will restart a little bit from scratch. So you can, of course, describe one or several defects in the specimen. Different defect types are available. It can be a planar defect, such as a delamination, such as a, I don't know, crack or notch or something like this. It can be also a cylindrical shape, such as a porosity, a cylindrical inclusion, for instance. And it can be also defined with a CAD shape, so an irregular shape, define another type of geometry for a certain defect, a volumetric defect. I will show you a bit later some examples with different defects. Let's start with a planar defect. So once you have selected the type of defect geometry, you define its dimensions, its length, its width, its thickness. Okay, so it can be quite thin if you want to simulate like an insert or a delamination, for instance. Then in the second tab, you define what the defect is made of. Is it just air? You can select air from the database of materials, or you can select a certain gas or certain also materials. In this case, Teflon is selected, so it's a Teflon insert defect, and its thermal properties of these materials are defined here. Teflon is also in the database. And finally, the positioning of the effect is defined in the third tab of this panel. So you can change the X, Y, and Z location. So X, Y, and Z. This is the depth of the defect. I put it here 1 millimeter. Okay, so my insert is 1 millimeter from the top surface of my component here. You can notice also that you can introduce here a certain tilt angle. So depending on the defect type, it can be relevant or not, but just to show you, I can here tilt and define a certain angle for my defect. And I here select 0 degree, horizontal orientation. Let's add two other defects, same dimension, same type, Teflon insert, but located at a different place and at a different depths. So second one is at 2 millimeters, this one, and another one on the right here at 3 millimeters to see what is difference between the response, the thermogram that we can obtain depending on the defect depths. It's nearly ready to run. I will just open the last panel, computation parameters. This is where you define here the simulation times, not only the heating time, but it's also maybe it can be a cooling time. So this is the observation time, and you need to simulate all the process from the start of the heating and the end of the cooling time, or if you consider an interesting observation time. So for instance, let's put 10 seconds. Then is a time step. So it means each time step, each 0.4, in this case, I will have one image. So it can be linked to your heat camera sampling frequency. It's also, of course, related to the simulation time steps that computes the heating process in the time domain, each time step. Here you also define the initial temperature of your sample. Let's start at ambient temperature, and let's put here 20 degrees. To simulate this, CIVA relies on a finite integration technique that needs to mesh the cross section of this component. So there is a mesh that is managed by CIVA. You don't have to really take care of the precise organization of the mesh, but you can act on the mesh by here a certain accuracy parameters, and also by defining this table, if relevant, some zone of refinement of the mesh. So you can actually visualize the mesh, the default mesh, for instance, and may change it if you want more accuracy when you start a certain study. So I will just here, I've enabled the mesh visualization. So it takes a few seconds to realize this mesh. From the mesh, I think, to share a new window so that you can see this visualization. Where is it? Here, there we go. Up. Okay, you should see normally a certain here an image. You can see a cross section of my specimen with a defect, and you can see some lines that show you the mesh that has been performed, and so refined on the mesh ends, and so it depends on the thickness and the position in depth of the different defects to make sure these discontinuity are properly accounted for by the simulation. Let's close that. In this case, I will keep this default mesh with this accuracy level, and we'll run the simulation. So it's in this case quite a simple case. I have not refined the mesh. I have just 3 defects, just 10 seconds of observation time, so it will be quite short, a few seconds. But let's mention that generally speaking, CIVA can reach quite fast computation times. But by the way, let's remind that it's a 2D simulation that is performed in this first version of CIVA TT. So course, a 3D would be a bit longer. Okay. After the calculation, the analysis page with the results is displayed. So let's maybe focus on some results. You have a thermogram view, you have a 3D view here, and you have a time signal window, and you have a cursor to put the time cursor to start to time 0, for instance. You can see here, if you change the cursor, that thermogram evaluates. So here, this is the temperature at this location of the cursor. I will put my cursor where there is some kind of discontinuity here. This is my first defect, and you can see that it appears. Okay, I'll go a bit further in time. I can shrink my my color scale up. Okay, okay. To visualize the defect, you can here see that I can see two defects that are on the left. Let's continue observations. Actually, I cannot really here see the third one, or really hardly actually, due to the depth of the defect. Let's project this thermogram on the 3D view so that you can relate the thermogram and the defect. You can see here the two first ones gives a contrast, not really the last one. Okay. So you can here see the fact that it's in 2D because here on this directions you can see that the contrast is quite sharp. So it's due to the fact that actually these edges are not really considered. You just take a cross section crossing the defect, then another computation is considered out of the defect. But here there is no 3D effect on these directions by definition actually in this version of CIVA. Okay, on this side, computation is performed. Okay, let's see also other interesting images. You can also display what is called a front view. A front view actually show you in two axes, both the x-axis and the time axis. So here, this is the time cursor. You can see that. Okay, start from the just after the pulse, the location where the more temperature, then the temperature slowly decrease, and you can see that after cooling, you can visualize, and on this view, it's maybe easier to identify where you can start to have some contrast because you have both the spatial and time cursor actually. So both aspects, and here you can see the first effect, and here the second one that is visible here. Okay, let's mention also that this signal curve, so which is, for instance, versus time in Cartesian scale, can be also here available in log scale. You have other image here. Also, you can take also the FFT of this signal, and so on. So this is basically the results you obtain from this simple simulation. With here 3 defects. In this case, we were in a reflection in a composite slab. Okay, let's try to see other examples, maybe. So I will load other cases. Let's try, for instance, to identify, to compare the response of different defects at different depths and maybe different defect sizes to see what you can. Oh, not this one. This one is the same one. Sorry, I want to load another case. Okay, so now we are here in transmission. Okay, heating source is on the top always, and we have here defined in this specimen carbon epoxy again, 3 millimeters thick, different defects on this block, 7 large defects like a delamination, let's say, same size but different depths. Okay, you can see. And then also in this line, 5 defects at the same depth but at different size, trying to see where is my limit of detectability for my current setup. Here, my source, so I've used Fresnel excitation, so like halogen lamps with 10-second heating time, and I've run the simulation in transmission in this case. Let's observe the results. Here, this is my thermogram at this time of the transient process. And so you can see here the heating and end of the heating process. Okay. My 3D view, you can again project your thermogram on the 3D view. So what you can see, you can see that actually you have a quite good detectability of the 7 large defects in this technique. If you consider the smaller defect, it may be not detectable anymore for the 2 smaller ones. Here you are at the limit typically of the defect. You can also see here the contrast with the cross section with the profiles, and to see here what you can have in terms of contrast. And so we have a bigger contrast, of course, with a large defect. And you can zoom in to evaluate a little bit the contrast in temperature between the defect and the free flow zones. Okay, so you have 2 profiles versus X or versus Z that can be analyzed, or versus Y, sorry, that can be analyzed. Here, this is I'm out of my object. So in this case, I can quite properly detect most of the defect, except maybe the 2 smaller ones in this case. Let's see what happens if now I consider same setup, but same components, but in reflection instead of transmission. Okay, same block, but detector is on the opposite side. Okay, so I've just put my cursor at time 0, and then you can see here I move my time cursor. Okay, you can see that the defect appears progressively, so I'm in reflection, so I can see first the highest defect, then the deepest defect appearing. Okay, I can shrink a little bit my color scale. Okay. Okay, to the end of the transient part, the coding parts. Okay, so I managed to see that one, but quite difficult to see actually the next one. So in this technique, maybe the deepest one becomes difficult to detect, and you can see that I have nothing for the line with a smaller defect in this case, and due to the depth of the defect in reflection in this case, I have less detection capability for the deepest defect. Let's see a pretty similar setup, but back in transmission, and also now considering, let's say, the same thickness, but another material inside the component. Okay, so let's say same defect locations, but now back in transmission, and above all, here I consider not anymore an homogeneous carbon epoxy multi-layers slab, but here I have considered that I have different layers with different materials between each layer. So you can see here, you can highlight each one individually. The lamination are located at the interplies each time. Okay, and here you can see that I have defined glass fiber, then aluminum, glass fiber, aluminum. So it's like a glare-like assembly, so metallic composites, heterogeneous assembly in this case. You can do that. You can do that, but what happens if you use the same setup in transmissions in this case. I open the results. Again, I can start at time 0. Okay, heating. Okay, you can see that a kind of contrast appears, but it's actually quite difficult to here to separate the defects actually due to the different materials. I have actually not anymore capacity to really separate the defect. In this case, you can see the image obtained at the end of the transient time. You have a kind of contrast for each defect lines, but actually you cannot really separate them anymore. The thermal wave is disturbed by this change of materials, and then you cannot anymore really identify the defect. So different cases, so different setup can be tested, such the one we have done here. Let's see other defect type. So I've mentioned that you can also define 2D CAD or cylindrical defect shapes. So for instance, you can define porosities, you can define all the type of defects. So here, in this case, it's again in a composite components, and we have here a certain group of defects here defined by like this cylindrical inclusion, but actually it's made of air, so we can consider it some kind of porosity distribution here with different size. You can see them. And let's compare the response of these porosities with other defects, such as delamination, for instance. Here we have defined delaminations, which is, let's say, distributed on several plies, not only at one interply, but different here, different sizes for different consecutive plies. And last defect, which is there, which is actually here a simple delamination, and another one here, which is a kind of a metallic insert in the composite slab. So simple delaminations, let's say multiple ply delaminations, metallic insert and porosities. Different type of defects here can be merged in the same simulation. Compare what I can detect and response. So let's here again describe and move the time cursor further, so the delamination are quite clearly visible. Okay, the insert is there as well, so delaminations. Zoom in a little bit. Okay, first delamination, nice simple delamination here. This is the profiles here. I insert, and here some porosities are detectable, or I can see something, but of course it's more difficult to identify them, and probably not all of them, depending on their size, can generate enough contrast to be detected on this thermogram. So a couple of examples. Let's also see some applications for metallic situations. Okay, in this case, we have a bilayer metallic specimen, kind of cladding maybe, on steel. So inconel steel assembly, and disbonding at the interface between both materials, one large one, one smaller one. In this case, we used Fresnel excitations. Okay, you can see the thermal response here. So in this case, we have a quite clear detection of the first disbanding. It's more difficult for the smaller one, but it's quite clearly visible. Again, you can compare the contrast with these profiles. Yeah, you can see the thermal shift, so about 6 degree contrast around this defect. Okay. You can also try to investigate maybe corrosion or crack detection on metallic component. Even if with crack, it's quite difficult with optical lens to detect. So in this case, for instance, we have put on the same setup quite big here irregular defect, which can model a kind of corrosion. Okay, on the opposite side. So to define this defect, actually we have selected the CAD shape of defect. You can draw a CAD sketch or import a CAD sketch to define a certain irregular shape like this for volumetric defect. Let's consider in this case it's air, so it's like a wall thickness loss, so it could simulate a kind of corrosion. And on the same test piece, we have put some planar defect, but maybe here quite wide, so like a big notch, wide notch, and smaller aperture, like more like a crack, or maybe here also we have investigated. We have put some planar defects to form like a branch defect in this specimen of aluminum. Okay, let's see the results. So corrosion is quite well detected. Okay, actually that's it. Cannot really see anything else with this setup. So the thin flow really in a metallic component cannot be really detected with this setup. Actually, of course, this is something that can be investigated further. But okay, again, a case where you can show defects that you can detect more or less easily, depending on the technique and depending on the type of defect. Okay, so it gives you an overview of the different type of possibilities in terms of specimen materials, specimen heterogeneity, type of defects, type of excitations, transmission or reflections, to see the different parameters you can play with in CIVA. If we talk about parameters, actually, when you run modeling, often this is not just one case, but maybe work on optimizations, or work maybe to try to detect the worst case or something like this, worst case scenario. So often it's a question of not just one setup, but varying parameter. So often you will need to perform some parametric studies. CIVA is quite well suited for that. Starting from a certain case, you can enable a parametric study here. It's something which is common to all modules within CIVA, UT, eddy current, and so on. If you do that, then you can pick up one parameter. I don't know which one, but one of the available is a menu here, for instance, that says the power of my heating source, and you can here select add to variation. You can do that for one parameter or for several parameters to define a kind of design of experiment. For instance, maybe, I don't know, let's select the width of my corrosion also as a varying parameter. So you can, like this, select some variable parameters, and then you have a panel in which you can monitor their variation range. Also, for instance, you can define for the power of heating, I want to study maybe 3 values between 1 kilowatts and 3 kilowatts. Okay, 1, 2, 3. Okay, And maybe for the extrusion, I can study 5 values going from 3 to 15 millimeters. So you can visualize also what it corresponds to. 3 different cases. And you are free also to assign other type of variations. You can define specific values. You can also select a kind of random distributions if you want to define a certain variability for the parameters. In this case, I have defined uniform distributions and in 20 cases for this parameter, if you consider it's an uncertain parameter. Doing so, you will run not one case, but several cases, and it will have in one CIVA files the different cases. This is one way to monitor parametric studies. Let's also mention that you can also monitor CIVA simulation through script. Instead of driving CIVA directly within the user interface, you also have a capability with CIVA script option to drive CIVA thanks to a Python or MATLAB script, for instance. Let's just take a quick example. So I don't know if you are familiar with this way of monitoring software, but actually here this is just a few lines of Python script. It's not that long actually in this case. You define, of course, the level of script that you want. And the idea with CIVA script is to be able to change the parameters in the CIVA simulations, to derive and launch a series of simulations, and to extract automatically the results. And thanks to the results you have extracted, also to define your own analysis process and maybe your own post-processing formulas, and all post-processing techniques can be applied by script in your Python script. Okay, so CIVA remains the simulator, but then you can drive that and maybe define several loops of modeling doing like this. So here on this example, so I drive here my CIVA parameters, and my input parameter is the emissivity of my component. I define here a list, just two in this case, 0.8 and 1, but you can imagine defining a wider range of variations. And after that, the results are extracted and the thermogram is reconstructed within Python, and you can also define your own criteria, plot some curves and so on, thanks to these tools. Let's launch it. So if you click on play, actually CIVA opens the case. You can this script change the values within the CIVA file, run the simulations in background, and will extract results and will display results in this window. So this is something also I wanted to share with you. This is one way to actually customize your CIVA studies, monitor them, and also maybe customize your analysis, the analysis of the results. You should see in a few seconds the first simulation. I think the first emissivity value, and then it will launch the second one. Okay, so it has extracted some results. It's a matrix actually of temperatures or digital levels of the thermogram. Then the thermogram has been built. It gives you the maximum, for instance, and then the second case is launched with another emissivity value and will be displayed at the end. So this is also a feature that can be connected to any modules within CIVA, the TT one, but also other modules of CIVA. Case, just let it finish and conclude here. There we go. Second case, another thermogram, and for instance, in this case, a curve that plots the temperature around the defect for the two cases. And of course, you can imagine other kind of process. Okay, this ends the presentation of CIVA features.